Another example of how to use a comparison test effectively is on a series like series n equals 1 to infinity, 1 plus sine square n, 5 to the n plus n. All right, so again, we're looking for quote unquote dominant terms. And that might help us, or it might help us to remember that sine squared of n at lowest is going to be 0, and at highest is going to be 1. Okay, and the reason for that is because, well, we know that the sine of n is between -1 and +1. So if we square it, it's certainly not going to get any bigger than 1. It's certainly not going to get any smaller than 0 if we square that. Okay, so when you're looking at those trig functions, it looks tricky, but just remember like the properties of your original trigonometric functions. And so what we can do is we can compare this to the series n equals 1 to infinity of 1 over, and then we clearly know that 5 to the n is going to get bigger than n quicker. Okay, so 5 to the n. So this is our b sub n. And then right here, this is our a sub n. And what we're going to do is we're just going to go through and look at what we did before. Okay, so we're going to have our n, and we're going to have an a sub n, which was equal to 1 plus sine square of n divided by 5 to the n plus n. And then we have 1 over 5 to the n, which is our b sub n. All right. And we're going to compare, let's see what happens with the terms. Now we're starting at 1, so maybe like 1, 2, 3, and 4, something like that. All right. Now I'm going to use my calculator. Okay. And remember, when we do this, we have to square the answer of the sine. So we're going to have sine of 1 squared, sine of 2 squared, etc. when we plug this in. Okay. So when we do this, we have, let me clear this out. Okay. So we're going to type in 1. All right, at least for this calculator. We're going to say sine of that value. Okay, so we have sine of that value. We're going to square it. I'm going to add 1. Okay. I'm not sure why it would square. Oh, square of that. Okay. So basically, the numerator is just about 1. Okay. Then we're going to divide it by 5 plus 1, which is going to be 6. All right. So approximately, we get 0.166. Okay. And over here, we know that this is going to be, when we substitute 1 in, that's going to be 1/5, which is 0.2. All right. So we know that 166 is less than 0.2. We'll do this a couple more times. So we're going to have sine of 2 and square it. All right. So clear all this out. We're going to type in a 2. We're going to take the sine of 2. And then we're going to square it. We're going to add 1. Okay, so we're just taking care of the numerator. All right, so we get 1.0012. And then if we take 5 squared is 25 plus 2, that's 27. So I'm going to divide this by 27. All right, and I get 0.037. Okay, now over here, we get 1/25. Okay, and we know that's 0.04. And we know that 0.037 is. So far, it looks like that a sub n is going to be less than b sub n. All right, we might just want to try one more, okay, just to be certain of this. So let's clear this. We're going to have 3. We're going to take the sine of 3. Okay, we're going to square it. And then we're going to add 1. Okay, and then 5 cubed is 125. 125 plus 3 is 128. So we're going to divide this by 128. All right, and that gives us 0.0078. Right, this gives us 1 over 125. All right, and 1 over 125. So clear this. We have 1 over 125, and that's going to give us a pretty. Oh, I divided that by accident. Sorry, I didn't clear it all the way out. So 1 over 125. And that gives us 0.008. All right, so, and we could keep doing this, but at least it looks like that a sub n is going to be less than b sub n. Okay, so For I, the sequence terms of a sub n are going to be less than or equal to b sub n, at least seemingly. Now, let's look at this series. Okay, so we need to know what's the behavior of the series n equals 1 to infinity of 1 over 5 to the n. Okay, well, one thing that we remember is that looks like a geometric series. And so we can rewrite this as the series n equals 1 to infinity of 1/5 to the n. And we go back and we think about our geometric series. Well, r is going to be equal to 1/5, which is clearly less than 1. So what that means is that we have a convergent geometric series. Okay, so this series converges. Okay, and then finally, by I and II, okay, the original series, n equals 1 to infinity of 1 plus sine square n divided by 5 to the n plus n converges by the comparison test. All right. Now, in the two examples that we've looked at so far, both of the series have been convergent. But let's take a look at the example of a divergent series. Okay. So once again, series n equals 2 to infinity. This time we have an n over the square root of n cubed minus 1. Let's compare this by looking at the dominant terms, n equals 2 to infinity. In the numerator, we just have n. All right, so we just leave n as n. And the only thing that we really care about here is, now think of this as n to the 3/2, right? If we change that into an exponent. Okay. And that's going to be the same as n to the 1/2 in the denominator after we simplify. So this is going to be the same as n equals 2 to infinity of 1 over n to the 1/2. This is a p series, okay? And the p series is going to diverge, okay? But eventually we'll get to that. But at this point, what we'd like to do is we'd like to compare the terms of the series. Okay, so just like we did before, we're going to have like a small table of values here. So we have like an n. Now we start at 2. So let's just maybe do the first 3. We have our a sub n, which is going to be n over the square root of n cubed minus 1. And then we have b sub n, which is going to be 1 over square root of n, or n to the 1/2. Okay, so we're just going to substitute these back into our calculator. Okay, so just going to do some rote computation. So we plug in 2. So let's just figure out what the denominator is first. So this is going to be 2 cubed. So it's the square root of 8 minus 1. Okay, so we're going to take the square root for 8 square root minus 1. Okay, so that's 1.828. So we're going to take 2 over that answer. Okay, so 2 divided by 1.828. All right, and that gives us 1.094. All right, and then we need 1 over square root of 2. So we're going to say 1 over 2 square root. Okay, and that's going to be equal to 0.707. All right, so this is bigger. All right, and then I guess what we could do is we could just figure out all the easy ones. All right, so let's do 1 over root 3 square root. Okay, and that's going to be 0.577. And then we know the square root of 4 is 2, so this is going to be 0.5 when we plug that in. All right, now over here, a little bit tougher because we're going to have to do a little bit of manipulation. So bear with me as we do this. And if you want, you can just do it in your calculator really quickly. So I'm going to do 3 to the 3rd, which is 27. So square root of 27 minus 1. And then I'm going to, this is 4.196. And then I'm going to take 3 over that number. So 3 over 4.196. and that gives me 0.715, clearly greater. And then if we plug 4 back in, now 4 is easy, all right, because we're going to end up with 4 over, this is the square root of 64. If we plug 4 in there, so that'll be 8 minus 1, which is 7, and then 4/7. So thankfully we got an easy one. So 4 over 7 is going to be 0.571, which is greater. Okay, so what we've seen in this one is that a sub n or b sub n is going to be less than or equal to a sub n, right? Now we look at the behavior of this series, right? And 2, we can say that the series n equals 2 to infinity of 1 over n to the 1/2. This is a p series where p is equal to 1/2, okay? And clearly 1/2 is going to be less than or equal to 1. So this series diverges, okay? And if we go all the way back up to the beginning, just to make sure, remember, if b sub n is less than a sub n, okay, which we just showed, okay, so b sub n is less than a sub n, check. And b sub n diverges, check. Okay, so that checks out. So that means by I and I, that means the original series, which was n equals 2 to infinity of n over the square root of n cubed minus 1 diverges by our comparison test. All right, so not too difficult, okay, really, when we do this. Again, just some basic computations just to make sure that maybe the first few terms follow either a sub n less than b sub n or b sub n less than a sub n. And then usually we have a really easy sort of test to perform, like a p-series or a geometric series. Sometimes it might be a really basic integral test. All right, and then we just use those results in tandem to determine if the series is convergent or divergent. Okay, now there are times where the series will diverge, but this might not necessarily be true. Okay, that's where we have to go to a different test because this test would be inconclusive. And one of those tests that we can lean on is going to be the limit comparison test. Okay, so that's what we're going to look at in our next series of videos.